Hello, my name is Andre Truxa, and for my Renewable Resources 580 course project, I will be assessing the reliability of 2-flux FA-PAR in relation to the known 6-flux FA-PAR. First of all, we must ask ourselves, what is FA-PAR? Well, it stands for fraction of absorbed photosynthetically active radiation. The last part, PAR, is the solar radiation in the range of 400 to 700 nanometers. FA-PAR is the fraction of that available PAR absorbed by the vegetation. PAR is important as increased levels promote plant growth. The importance of PAR is very well described here in the slide, with a quote taken directly from the website of the Global Climate Observing System, who hold this variable in such high regard that it has been deemed an essential climate variable, or ECV. This is the current way we measure in situ FA-PAR. In the study, values measured from this calculation with these sensors are considered true values, as they have proven in the past to be a reliable source for the ground measurement of FA-PAR. This can lead to quite the headache in the field, as an intricate and sophisticated setup with all these sensors can be very labor and cost expensive. 2-flux FA-PAR is the responding variable and the new methodology we are testing in the study. The transmitted PAR sensors are located in the forest, while the incoming PAR is in a nearby field where tree canopy cannot interrupt the incoming solar radiation. Should this method prove to be reliable, it would be a more cost-effective and labor-effective method for in situ FA-PAR measurements. Based on a past study done in the evergreen forest of Germany, we expect that 2-flux FA-PAR shows to be a reliable source of ground measurement. As the other objective of this study, we will be assessing the variability of the accuracy under different weather conditions. The study area for this project is Santa Rosa National Park in Costa Rica, located in the northwest corner of the country. The biome for this study is the tropical dry forest. On this map, you can clearly see the points denoting the location of the wireless sensor network. You may notice one point clearly separate from the rest. This is the incoming solar sensor, which is taken in a field, not to be blocked by forest canopy. You may also be wondering why we did not bring the other sensors closer to the incoming solar sensor. And this was a conscious decision with the hopes of diminishing the horizontal fluxes. All sensors were set at a height of 1.3 meters, with 4 transmitted sensors allowing 4 measurements to be taken at a time, from which the average was then calculated. This study took place from April 30th to July 9th of this year, with measurements being recorded in intervals of 15 minutes. In this analysis, we are only using data from 11 a.m. to 1 p.m. to avoid too much variability. In addition, temperature and precipitation were collected at a weather station in Santa Rosa, and solar angle was collected daily by a field assistant. Quick look at the data I input into R. Here are the initial distributions of the FA-PAR data for the true and the mean of the test data. As we can see here, the data is not normal. The true and test data are both heavily skewed to the right. It must also be noted that the true FA-PAR shows some bimodal tendencies. Since this is a comparison question, I also took a look at the distribution of the difference between true and test, which led to a normal distribution. Here are the box plots for the true and test FA-PAR. As you can see, there are no major outliers, and here is the box plot for the difference, with a few outliers on both ends. Included as well are some descriptive statistics of all the fields. To answer the first question of this analysis, I plotted the 2-flux FA-PAR to the 6-flux FA-PAR. Since the Pearson correlation coefficient was around 0.72, which is right on the verge of being a strong correlation, I conducted a simple linear regression hypothesis test just to make sure. As you can see, the p-value was very small. This leads me to my first conclusion that we can be 95% confident that 2-flux FA-PAR is a reliable source for in situ FA-PAR measurements. The second part of the analysis is finding out if weather conditions have an effect on the accuracy of 2-flux FA-PAR. So here we plotted the difference between the true and test value with temperature, precipitation, and solar angle. Here we can see with a multiple linear regression hypothesis test that temperature and precipitation present high p-values, whereas solar angle presents one lower than the alpha level. This low p-value leads me to my second conclusion that while there is no significant temperature or precipitation effect on the difference between 2-flux and 6-flux FA-PAR, we can be 95% confident that solar angle has an effect on the difference between 2-flux and 6-flux measurements. This means that there may be parts of the year where 2-flux FA-PAR is not an accurate alternative. To recap, this analysis found that 2-flux FA-PAR, the cheaper, more efficient alternative to 6-flux FA-PAR, measures the metric accurately. In addition, it found that temperature and precipitation do not affect the accuracy of 2-flux, but solar angle, on the